theorem. So what are we going to do? So we're going to understand and use Stokes' theorem, use a curl to analyze the motion of a rotating liquid. And well, so again, from the two-dimensional idea that is Green's theorem, well, which is essentially related to a line integral, well, the one that gives us the, in this case, this is the curl version, this is the 2D or the two-dimensional curl. And the two-dimensional curl, again, well, we're adding all those curls, all those micro circulations in a region, and that's going to give us the total circulation around the boundary, right? So, and you know, the usual f is composed by two functions, g of x, y, z. Well, in this case, it's just f and g of x and y, actually, the 2D version. And well, you know, C is the boundary of the region and of the region R. Now, we're going to take this into the third dimension. Well, so essentially we're going to create this solid here. But this time we're going to do, well, essentially the same. We're going to look at the circulation on the surface, not on a planar region, and knowing that C is actually a boundary on the surface, all right? So essentially what we're going to do is relate, so we're going to relate or find the relationships between a surface integral over an oriented surface S and a line integral over the surface Q as shown in the figure, right? Well, so this is what we got for Green's theorem in two dimensions. So that is essentially the curl in two dimensions and in the direction of K, because essentially we did this calculation over a planar region. I mean, this is the xy plane. The curl is going to give us that orthogonal, a vector that is orthogonal to that plane. So that's why we simply get K. Now, if this plane is turned into a surface, now check how in this case. Well, in this case here, this normal vector in the direction of K, in the direction of K, or in the direction of Z, if you will. However, in 3D, it's not just going to be a vector in the direction of K, but it's going to be a vector in the direction or in multiple directions. So in this case, we are going to generalize this to some vector, a normal vector that we will call N. All right? And well, as far as the orientation of a surface, again, so you can think of your paper as a surface. You put a vector that is normal to your paper, grasp the vector, you will see your fingers curling counterclockwise. All right, so that means the positive orientation in this case. That's the right-hand rule. And well, what's the Stokes' theorem? Well, in general, I mean the definition. So we have S surface oriented in R3 with a piecewise smooth closed boundary C, whose orientation is consistent with that of the surface X. And we're going to have a vector field composed by F, G, and H, and that vector field has the continuous first partial derivatives on the domain of the surface. Well, so in this case, this is how we relate this line integral. So we will, instead of evaluating a line integral for which we would have to parameterize, you know, all it takes to evaluate a line integral. So instead, we're going to evaluate surface integral of, in this case, well, the curl of f, which in this case, right here, we can simply say, all right, this is essentially, well, nabla cross f. It's the same as saying curl of the vector field f dotted with n ds. And yes, you might be thinking, yeah, do we really have to find those normal vectors? Well, no, we got that last time. You know how the magnitude of the gradient, so we divide that gradient over its magnitude to get those normal vectors. However, ds, which is the element of surface area for the double integral, well, essentially those quantities really cancel, and in the end, all we have to do is evaluate this integral right here. And by the way, again, this is something I mentioned last time about the notation the textbook uses. So notice our vector field F is comprised by the components F, G, and H. The G that you see in the surface integral right here, careful, it's not the same G. It's so let me just change the notation here. So this is really negative Z with respect X, negative Z with respect Y. So it's the surface that we define in terms of the variables Z in this case. All right. Let's see, how about we look at one example. So let's use the Stokes' theorem to evaluate the line integral of f dotted with dr if the vector field f is given by 4y, negative 2x, and 5. And as the surface is the upper half of the sphere, x squared plus y squared plus z squared equals to 25. And C is the circle, x squared plus y squared equals 25 again. Let's go back to the definition of Stokes' theorem and check something pretty interesting here, just to check for some consistency. And in this case, the boundary C, its orientation is consistent with that of S. So in this case, well, this circle right here, which the circle of radius 5, that x squared plus y squared equals 25, it's actually the projection in the xy plane of the sphere, right? So yes, this circle will indeed be a boundary on the sphere, right? So let's, so number one, let's find the curl of f. So curl of f, that's actually nabla cross the vector field f. So that's 4y, negative 2x, and 5. And that's I, J, and K. And what do we have? So partial with respect x, partial with respect y, and partial with respect z. Well, after doing this cross product between the nabla operator and the corresponding element or components of the vector field, we should get the following vectors. So just to save time, so we should get the vector 0, 0, 6. Okay? So that's the first part, the first thing we do, find the curl. And number two, well, we need to observe our surface. Well, so what do we have for the surface? So number two, we have S, which is x squared plus y squared plus z squared equals to 25. Well, solve for z, because again, careful with surface integrals. Recall that surface integrals have this little pitfall that in this case we're evaluating an integral over dA, that is in 2 dimensions essentially. And if you have that third variable, you need to write it in terms of x and y, which is what we're going to do here. So that's z squared equals 25 minus x squared minus y squared. And z equals to the square root, well, plus or minus essentially. But notice they're telling us that it is only the upper half of the sphere. So I'm just going to write the positive solution here. So 25 minus x squared minus y squared. And well, so we need to take the partial derivative of this function z because we need those two pieces of information in our surface integral. All right, so, and that is, it's this part, right? Let me highlight what I'm going to do. So I'm going to compute these two quantities. The partial of the surface, of the equation of the surface, with respect x and with respect y. So I would like to rewrite this as 25 minus x squared minus y squared to the 1/2. And partial of z with respect x, that's going to be 1/2 25 minus x squared minus y squared to the negative 1/2. And by mini chain rule, we differentiate the quantity inside of the parentheses with respect to x. That is 25 and y. Everything else is constant. So in this case, times negative 2x. And check how the 2's cancel right here. And that's going to leave us with x divided by 25 minus x squared minus y squared to the 1/2. And we may go back to radical form. That is x over 25, or the square root of 25 minus x squared minus y squared. And that's the partial of z with respect to x. We also need, yes. Which one? Oh yeah, this is negative. Thank you. Negative. And similarly, the partial of z with respect to y, that's going to give us the same thing essentially, except that the negative x will be negative y. So 25 minus x squared minus y squared. And you can verify this. If you do the same work I did with the previous one, you should get the same thing. Number 3, evaluate the surface integral. Well, the line integral via the surface integral. So instead of parameterizing anything, which we could, because we have a circle of radius 5, we can come up with a combination of cosines and sines, But well, the idea is to use the surface area here. So number 3, what do we have? The integral of f dotted with dr, which instead we're going to evaluate it via the double integral of nabla cross f, that times dot product with negative z with respect to x, negative z with respect to y, comma 1, and with respect, and let me call this dA. Yes, this is dA for now. All right. Okay, so we already got nabla cross f, which is what we did before. That's the vector, double integral of the vector 0, 0, 6. Dotted will, careful here, because in the element of surface area, the partial derivatives are negative, and well, because of this negative sign right here, that's going to cancel that negative sign there, right? And well, in this case, so that's going to be x over the square root of 25 minus x squared minus y squared, comma y, square root of 25 minus x squared minus y squared, comma 1, and let me still call this dA. All right? So number 1, next step would be to do this dot product, and again, to perform the dot product, we multiply component by component. The x component of the first vector times the first component of the second vector, and then the second component of the first vector times the second component of the second vector, etc. But check what's going to happen. So 0 times this madness is going to be 0. Plus 0 times this other madness, it's also 0. And 6 times 1, 6 dA, which in this case is going to be the double integral of 6 dA, which is 6 times the double integral of dA. But we don't need to parameterize anything or to iterate this integral, because guess what? This region is over which we're integrating is circular, isn't it? And all we have to do is find the area of the circle. That's it. So 6 times the area of the circle which is in this case 6 times pi r squared, and the radius is 5. That is 5 squared, which is 25, and 25 times, and I think I'm missing a negative, am I? I got the feeling, no.
We want half pi r squared, we're only doing half circle.
Mm-hmm. Half of the oh well, no, it's half of the sphere, but projected onto the xy plane. That actually includes the whole circle. Mm-hmm. And well, that's 6 times. I'm pretty sure. Okay, never mind. I thought I had a negative here. So, and that's 150 pi. All right, 150 pi. So that's one example of how we use the Stokes' theorem to evaluate a line integral again, but instead of evaluating a line integral, parameterizing, notice we didn't parameterize anything. Actually, well, it still took a good minute to go, because we evaluated a surface integral. We still had to evaluate to compute some partial derivatives and the like, but in the end, everything reduced to finding the area of the region and multiply by this coefficient. All right, let's look at another example. For the next example, let's use Stokes' theorem to obtain the circulation if we let C be the oriented triangle lying on the plane given by the equation 2x plus 2y plus z equals to 6, as shown in the figure below. And of course, we need to know a force field given by 2yz, comma xyz, comma e to the z, or what is it? Yeah, e to the z. Well, now think about this. If we were to parameterize C1 and then C2 and then C3, which we can, that's just going to take forever to do. But in this case, instead, we can use Stokes' theorem, evaluate the surface integral, which is a double integral, and it's going to take a lot less work than parameterizing 3 different paths. All right. So let's see. Number 1, well, now that we have this surface here, I'm going to solve for z. That's 6 minus 2x minus 2y. And from here, I'm going to take the partial derivatives, partial of z with respect x, which is negative 2, and partial of z with respect y, that's also negative 2. All right? Now, because in this case, we will require to evaluate a double integral, that is an integral over a planar region, we need to understand what's going on in the xy plane, which in this case is this projection here, and it's actually labeled for us as R. All right? So this triangular part right here, let me take it over here, that's going to be this triangle here. And in fact, well, they also were very nice. They just gave us the x-intercept, so that's 3 and 3. That's the region. Make it look like a line. All right. And that's actually, well, y equals to, well, what do we have? Negative x, because it's a negative slope, negative 3 over 3, that's a negative 1, and a y-intercept of 3, so plus 3. So that's the equation. That's how we will iterate the integral later. And in fact, well, we can iterate the region, or iterate the integral rather, in this case, whether as vertically simple or horizontally simple, either way. But we usually go with the vertically simple idea, because that's what we work with functions of x rather. So we integrate first with respect y, and then with respect x. There's nothing wrong with doing it the other way. It's just how we are used to do it, right? Unless we had a more complicated region, well, we will have to go the other way. All right, so let's see. Let's find the curl of f. So the curl of f, that is nabla cross f, and that's the components of the vector, which is 2y minus z and xyz and e to the z. and that's I, j, and k. And well, here we have the partial derivative operators: partial with respect x, partial with respect y, and partial with respect z. And well, after doing this, this determinant, this 3 by 3 determinant, which gives us the curl, we should get the following vector: negative xy, comma, negative 1, comma, yz minus 2. All right? And so that's the second part. Now the third part is to actually evaluate the line integral, but in this case via the surface integral. So number 3, that's the integral over c f dr equals the double integral over r of the vector f, the vector field f actually. Well, let me write actually the definition first. So that's a curl f, and dotted with, I have it here, I have the formula here, okay, negative z over part with respect x, negative z with respect y, comma 1, dA. So we're going to evaluate it this way instead. So the curl of f, which we already have, I'm going to go to the next line. That's the integral over the region R. The curl of f, okay, let me highlight this. This is the curl of f. It's going to go here. And these partial derivatives that we already calculated, that we already found before, are going to go over here. But careful with the signs again. Be careful with them. All right? Because we have for the two partial derivatives we got negative 2. However, in the formula, those negatives will cancel those negatives to turn them into positives, and that's going to be the curl, well, the curl which is, whoops. Negative x, y, comma, negative 1, yz minus 2. And that times the partial derivative, negative the partial derivative with respect to x, which is 2, negative the partial derivative with respect to y, which is also 2, and the one that also comes from the formula, dA. Now, be careful, because when we iterate this integral, again, this dA, okay, let me make a quick note over here. This dA essentially is dy dx, all right, or dx dy, depending on how you want to iterate the integral. However, notice the integrand contains a z over here. That's the issue, so that's the one that we need to get rid of by writing it in terms of x and y. How do we do that? Well, look at the surface over we are working on, in this case the surface given by the equation of the plane, and we already solved for z. Okay, so let me highlight it so you can see what am I going to do here. So I'm going to highlight this z right here. That's going to be this z right here, all right? That equation. So let's just substitute it in there. And that's going to be the double integral over, oh, that's number 1, negative 2xy minus 2 plus yz, but careful with the z, so we're going to replace it with the quantity 6 minus 2x minus 2y, and let me highlight it again with the same color so you can keeping track of what am I doing here. So when you go see the video again, so you can see all this again via color coding here. And, well, actually, I'm going to change this negative 2 with a negative 4, because I think I forgot a minus. Oh, you know what? Never mind. I'm going to keep this negative 2 minus 2. And And what did I do? Did I compute everything already? Oh yes, so essentially this should be parentheses because I'm also doing the dot product at the same time, all right? So negative xy times 2, negative 2xy. I forgot to explain that part. And negative 1 times 2, that's a negative 2. And this quantity times 1, it's the same quantity, but at the same time, I'm replacing the z with the equation that depends on x and y. So in the next step, so that's going to be the double integral, and I think I'm going to leave space over here for the limits. So that's going to be negative 2xy plus or minus 4 plus 6y minus 2xy and minus 2y squared. I'm gonna write the a still. We can still combine some terms because we have those two negative 2xy's that we can simply negative 4 actually. 4xy minus 4 plus 6y and minus y squared. And I think we can do the dy dx already because we have the integrand rather already simplified. Yes?
It's a minus 2y squared.
Minus 2y squared, right? Where is, yes, minus 2. Thank you. And well, so if I remember well, we decided to go the vertically simple way. All right? So in this case, let's look at the region. It's vertically simple. So it's bounded above by the line and below by y equals to 0, and from x goes from 0 to 3. All right? So that's going to go from 0 to that equation of the line. That's a 3 minus x to 0 to 3. Okay? And well, I'm not going to do this double integral. It has a lot of terms. I mean, I think at this point we know how this works. I mean, so I'm just going to give you the answer. Should be negative 18. Right? So this means the circulation is negative. Right? Okay, so for the last example for this section, let's see. They're asking us to verify Stokes' theorem. So whenever you see the word verify, that means they're asking you to solve the problem using both sides of the formula. Solve it in this case, for example. Let me go about the Stokes' theorem. So number one, that's the line integral over C of f dotted with dr equal to the double integral of, let me get it again, the double integral of nabla cross f dotted with n ds. In this case, that means we are going to solve the problem both ways in this case. All right? So the first way, okay, number one, what's the problem about before we get to solve the problem? So number one, so we have this surface S, which is the hemisphere x squared plus y squared plus z squared. How do we know it's a hemisphere? Well, they're not telling us which one is it, the upper or the lower, but we're going to know that it's going to be the upper hemisphere because of this condition here. Z is greater than or equal to 0. That means we want the upper hemisphere. So, and C, which is the boundary around the surface, that's that's whatever trace it is. Notice the information they're giving us this time. It's a little cryptic. It's not as straightforward as in the previous example. What was that? Number one. So they literally told us, okay, is the sphere is the upper hemisphere, and well, the boundary C is the circle of radius 5. You know that it's also the boundary of on the sphere. However, here it's a little cryptic But in this case, they're telling it it's a trace. Remember traces from the beginning of the semester? So that's when we make one of the variables 0. And in this case, well, it's a trace about the xy plane, right? So that means, again, it's consistent with this, with z equals to 0. You know, all this vocabulary, all these different ways to present this kind of problems, right? It's same thing. Well, all right. So the vector field, the force field is F equals to vector field z minus y comma x comma negative x. Okay, so let's compute the circulation by evaluating the line integral. So this time we do the line integral first. All right? So let's see. By line integral, in this case we're going to evaluate the integral over c of f dotted with dr. All right? Well, what is c anyway? Well, so let's go to the plane first. Let's go back to 2D. So c in this case is the xy trace of the sphere, which in this case is really the circle of radius. In this case it is 4, isn't it? I mean, no, the radius is 2, but the radius squared is 4. Well, let's draw that circle, and here we should be specified that z equals 0. All right, that's what it means to get the trace, right? It's the xy trace. Well, so from here, well, we need to parameterize, yes, because it's a line integral. They're asking us to do it first by parameterizing. So that's r, which is, well, we can parameterize a circle, r of t. You know the different ways to parameterize a circle. It's either cosine or sine comma cosine, but depending on the orientation. In this case, orientation matters because, again, we're going in the positive orientation. That means counterclockwise. So which one is going to go first, cosine or sine, or vice versa? Cosine. Cosine, right? So cosine t, sine t, but this would be the parameterization of the unit circle. We're not working with the unit circle. This is a circle of radius 2, so just multiply this by 2. All right? Again, as a brief review for line integrals, we need to find the derivative of this vector valued function and find its magnitude. That is negative 2 sine t, 2 cosine t. And, well, again, recall that in this case, well, this is going to be valued for t between 0 and 2 pi. That's where this path gets traversed once. All right, well, let's see what else we have. So now we're going to evaluate this. Do we need the magnitude? No, we don't need the magnitude here. I don't think we need it. It's just a derivative, all right? So,
third component.
Yes, that's what I was going to mention because hold on, yes. So let me write down the integral. Hey, what happened here? All right. And so this is actually going to be the integral over c of f, which in this case is z minus y, comma x comma negative x dotted with something's missing here, negative 2 sine, okay, let me write down what we have, negative 2 sine t comma 2 cosine t. We cannot perform the dot product between a vector in R3 and a vector in R2. It's not possible to do that, but well, the solution to this is to just add a 0 to the parameterization that we had before. All right, so, and only then, yes, now, problem solved, and dt. Okay, so let's see. Well, that's going to be number 1. Careful, because what do we have over here? Remember this 0 equals to 0. So this will be a 0 as well. So that's the integral from 0 to 2 pi of 0 minus sine, or minus 2 sine t. Where am I getting this 2 sine t? Because this y right here is the same y as the vector valued function. And comma x, which in this case is 2 cosine t, and negative x, that is negative 2 cosine t, dotted with, let me make some room over here. And let me make this look like an actual vector, yes. And that's a negative 2 sine t, 2 cosine t, 0 dt. All right, so dot product, component by component, that's going to be, okay, negative 2 sine times itself, that's actually 4 sine squared. 2 cosine times itself, 4 cosine t squared rather. And negative 2 cosine t times 0 is just going to be 0 dt. But do you notice the identity sine squared plus cosine squared? Isn't that just 1? But times 4, that's the integral of 4 dt from 0 to 2 pi. And that should be equal to 8 pi. All right. So after all, it was not that hard to do it the parametric way, right? So that's part A of the problem. Do it the parametric way. Now, part B of the problem, to solve the same problem, however, using Stokes' theorem in this case. So do the same problem again using Stokes' theorem and verify that the result is exactly the same. And well, so number 1. Okay, let me write the surface. Okay, it was a hemisphere in this case. So x squared plus y squared plus z squared. And in this case equals to 4. But in this case with the condition that z is only greater than equal to 0. That's what denotes that we're working on the upper hemisphere. All right, so let's solve the equation for z. Z squared equals 4 minus x squared minus y squared. And z, I know when we use the square root property, technically we should have that plus minus. But in this case, because of this condition, that we're only working on the upper hemisphere, we just take the positive radical, right? Okay, what's next? Well, take the partial derivatives that we need. So that's the partial of z with respect x. And actually, we already did something similar to this. That's going to be negative x over the square root of 4 minus x squared minus y squared. And the partial derivative of z with respect to y, that's a negative y over the square root of 4 minus x squared, oops, forgot the minus y squared. We got almost everything we need. What else? Okay, so we have, okay, so the region over we're integrating, that is the C. That is, oh, come on. That's the circular region for x squared plus y squared equals to 4. All right? And, well, so the circular integral of, that is of C f dr. So we already did it this way, the parametric form. But this time we're going to go about, oh, I don't think I found the curl. I need to find the curl first. Hold on. So number 1, that's curl of f, the curl of the vector field, which is nabla crossed with f. That is. Let me write down the components of the vector field. That's z minus y and x and negative x. I, j, and k. And well, the second row of this matrix here, it's the partial derivative operators with respect x. with respect to y and with respect z. And well, after doing this cross product, that should give us the vector 0, 2, and 2. And again, I'm doing this just to save time because doing this determinant is going to take a good minute to go. You can either use a formula for a curl, you have a formula for a curl, or you can repeat the first two columns, which is a trick I showed you at the beginning of the semester. Either way, all right? And well, so now that we have everything we need, so that's the line integral over C of f dotted with dr. That's actually the double integral of the curl nabla cross f dotted with negative the partial of with respect to z, comma negative the partial of z with respect to y, comma 1, dA. Okay, and let's call it R for now, which is going to be this region R. That's the region generated by this xy trace from our surface we're working on. Well, so we already got this cross product, the curl, which is going to be this guy right here, and we got our partials from before. That is, these two, and that's going to be this one and this one right there. Pretty much substitute whatever it corresponds where it corresponds. That is the double integral dot product between the curl, which is 0, 2, and 2, dotted with, that's going to be negative x root over 4 minus x squared minus y squared, comma negative y over root of 4 minus x squared minus y squared, comma 1 dA for now. All right, we will see how we will iterate this integral. So the next step is to do the dot product component by component. 0 times this first component, that's going to get zeroed out. 0, and then 2 times the y component, that's going to be negative 2x, 2y. Oh, yes. Thank you. You know, you see how I made a mistake. Didn't want you guys to do. Thank you. Good catch. So that's plus 2 or y over the square root of 4 minus x squared and minus y squared, comma 1 times 2, that equals to 2 dA. All right. Okay, let me clear the 0, some symbols here. That's the double integral over R of 2y over the square root of 4 minus x squared minus y squared plus 2 dA. All right. Now, here is the thing. So here is the integral that we get to evaluate. So it's an integral that contains x squares and y squares, right? And we're also integrating over a circular region here. So I think this is a good candidate for a polar, right? For polar coordinates. So we know the identities over here. So this y right here will become r sine theta, and this negative x squared minus y squared is going to be negative r squared. And what's dA going to be? R d theta, right? So let's go ahead and iterate this, and transform rather this integral. So number one, let's look at the region. So in polar, this circle right here essentially is telling us that r is varying between 0 and 2 and theta, because in this case, well, they're not conditioning anything about, oh, it's the first octant or anything. Essentially, it's around the whole circle. That means theta is varying between 0 and 2 pi. All right? So let's write down the integral. And that is the double integral from 0 to 2 pi. Oh, wait, no, from 0 to 2 first, and then 0 to 2 pi. That's 2r sine theta over the square root of 4 minus r squared. Oops. And plus 2 r dr d theta. Okay, let's simplify it just a little bit. So that'll be the double integral from 0 to 2 pi and from 0 to 2. And just essentially what I'm going to do here is distribute the 2. Multiply the r and multiply the r with the 2. So that's 2r squared sine theta over the square root of 4 minus r squared and plus 2r. Now, let's observe this integral. If we do, yes?
Wouldn't the partial derivative be 2x and 2y over the square root?
Oh, yes, but in this case, since, well, this is similar to what we did before over here. Let me go back. So I think it's the first example. So yes, so technically there's a mini chain rule, but that 2 cancels with the 1 from the rational exponent, right? And okay, let's observe that integral right here. I mean, if we evaluate with respect r, it's not going to be that easy, I'm afraid. It looks like we would have to do some weird substitution or trigonometric substitution. So if we had r to the first power, u sub would have worked really, really nicely, right? We can do it something else. We can actually reverse the order to d theta dr. And in this case, it would be really easy to reverse the order because the limits of integration, in this case, they're constant values. So when that happens, you can reverse at will. However, when the limits are variable, then you will have to look at the region of integration and look at all those equations that describe or define the boundary and rewrite all the equations in terms of the other variable. But it's not the case in this situation. So this will be the double integral first from 0 to 2, 0 to 2 pi, and that's the same integrand. Plus 2r and d theta dr. And well, that's still going to take a good minute to go in the end. Well, you know what the value of the integral should be, isn't it? 8 pi should be the same as we did it before. And well, I mean, I know what you might be thinking. So isn't it? So I mean, if you are looking at this pattern, isn't it true that every new topic that we're learning in this chapter, it's the easier version of what we did before? Well, in this case, well, there's exceptions. So in this case, it looks like Stokes' theorem makes the problem harder than actually evaluating the line integral by parameterizing. So there's situations, you know, and stuff happens every now and then.